I can't figure out why it just decides to stop. All right, good. It probably shouldn't stop anymore. All right, so the first question about sort of whether or not we're measuring our constructs well is about reliability. Are you measuring anything real about this person at all? Or does your test just measure random stuff? Like how cold it is in the room. Random stuff like today you had a piece of a stone in your shoe. Or random stuff like today you happen to have gotten not enough sleep, but tomorrow you get plenty of sleep. How sensitive is your test to random crap that is not repeatable? That would not repeat if you gave the test again and again and again. That's about consistency, the reliability of the test. And so we call true things about you that would influence your scores on any test, we call those ideas your true score on that test. And that's called true and error score theory, classical test theory, which we covered a little bit of. Right? And so if a test is measuring real things about you, it will be reliable, because then you'll get the same score over and over again. Does that make sense? If the test is measuring real things about you and not random crap like flies buzzing by and how cold the room is, if it's measuring real things about you, you'll get the same score over and over again, over time as well as within the test. And so we can think about your score on a test as being a function of true stuff about you and error. Error is all that other random crap that's influencing your test score today that won't influence your test score tomorrow, right? And we thought about this in terms of a ratio. You remember that?
Is it true over observed plus error?
That's right. It's true over observed plus if that ratio is really big, that's a good thing, right? Observed is actually T and E. So it's true over observed, but observed is a function of your true score plus error. So it's T over O, right? So if that ratio is really big, that's a good thing. If most of your test score is true things about you, that's a good thing for reliability, right? For reliability, you want the ratio of truth to observed to be really high. And there's not like 5,000 items on the test, but it does show up, right? There are some easy items and some rigorous items. But classical test theory doesn't care what's true about you, right? Because that's a different question. Because a test can be highly reliable even if it doesn't measure what you say it does, right? Right? You can have your ratio of truth to observed be super high and still be measuring crap. You're just measuring true crap. True things about you, like your test anxiety, like the fact that you're chronically depressed, which affects your test score too, right? You can have a highly reliable test. Your observed score is mostly a function of your true score, and it still not be measuring what you say you're measuring, right?
Is that validity?
That's validity. Does that make sense? Validity is about gathering evidence that you are whatever interpretation you're going to make on this test score, that interpretation is a good interpretation, right? So let's say I design tests that are so bad, people are just guessing. They're like, right? That would not be reliable even, right? But let's say I measure tests and you're not guessing, you're trying really hard, but they're so difficult that a lot of your test score is your test anxiety. Some people do better because they handle their stress better. I would have a highly reliable test that has questionable what? Validity. Or remember my example of long-term successful cheaters. The amount of truth I'm measuring about them is really high. Right? Truth over observed is really high. Most of their test score is a function of true things, but what? What's true about them? How will they cheat? Does that make sense? Validity is about what you're measuring, the interpretation. And there's evidence that we gather to establish validity, right?
If you gave bad tests and they were consistently really bad, and you would consistently measure how...
It's about whether or not the same person will get the same score again. That's consistency, right? So if I give you a test that is just a terrible test
Yeah.
because it makes you so stressed out.
Yeah.
Could be super reliable. Because is your stress always going to impact your score? Yeah, your stress is always going to impact your score. Perfectly reliable, just not particularly valid. Does that make sense? These are two questions we can ask. So you can think of reliability as a bare minimum. Measure real stuff and not random stuff. Measure something that would continuously always influence the person's score. That's reliability. Measure what you say you're measuring. Interpret that test score as reflecting the knowledge in the class. That's a separate question. Validity.
Right.
And there's evidence to establish validity, right? There's content validity. What's that?
Stuff on the test is actually related to what you want to measure.
But not just that. Yes, the stuff actually relates to the test. The items reflect real things, but all the universe of things, right? That the content is exhaustive. That you've measured all the different facets of whatever it is you're trying to measure. And the example I used in here, one of the examples is how they used to measure aggression. Aggression in children used to be only be measured in terms of physical, obvious aggression. Hitting and yelling and pushing and screaming. Right? And for a long time, that was how they defined aggression. Now that arguably had poor content validity. Because anyone who's seen the movie Mean Girls knows there's so many other ways to be aggressive that have nothing to do with physical aggression. Right? And so there was poor content validity. And it took a long time for sort of the understanding of aggression to grow and change and have better content validity for the measurement of that construct. So construct validity, which is are you measuring what you say you are, and validity in general, which is are you interpreting this test score in a valid way, is a never-ending process of gathering evidence. That you're actually measuring what you think you are, that you covered the entirety of the construct. And we talk about face validity too, right? Do the measures seem good? Do they seem like good items? That is face validity. And the last validity we talked about was criterion-related validity. And that's that your test predicts things that it ought to. Like the SAT actually predicts how well you do in college. That would be criterion-related validity. The criteria of college success is related to the test. Criterion-related validity. Like if you have a test of depression that measures how depressed you are, it should be related to whether or not you actually can get a diagnosis. With higher scores on a test of depression, predicting whether or not a clinician actually diagnoses you with depression. Criterion-related validity. Be able to recognize scenarios that would fall into those different types of validity. Yeah? So know the goods and bad things of the mean, median, and mode, right? Talked about each of those in turn. Understand conceptually what an average is, conceptually what a median is. So I might ask you questions about the median, right? I might ask you about the basic definitions. What's some bad things about the mode?
All it cares about is the number that cares most, doesn't care about anything else.
Yeah, so there's a considerable loss of information when we just report the mode. All we're reporting is the most frequent value, and we ignore everybody else. There's a loss of information. What else? There were two other bad things. Would we ever want to use a sample mode to estimate a population mode?
No.
No, because we said that the mode was biased. The mode is almost always pretty unique to your individual sample. So it's a very biased statistic. It can describe your sample, but unless you have a very, very large sample, it's usually biased.
The mode?
Yeah. And it's not used in inferential statistic, right? We haven't even got to inferential statistics yet, but you should know we don't use it to make decisions about populations. Good things about the mode, though.
It's easy to calculate.
Super easy. You just go, there it is. Well, certainly if we have discrete data, right? If we have discrete, well, it's also easy to find, right? If you have discrete data, you just put your numbers in order and look for the one that shows up the most, right? And it will actually occur in the data set, which is cool. If you have truly continuous data, where every single person has their own unique value, there's still a mode, right? It's the most probable value, and that's super easy to find. You just find the top of the graph. Yep, there it is. There's the mode. And it has a neat mathematical property where the slope of that density function will be 0. The mode will be where that slope is 0. Yes?
You said there was 3 bad things about the mode. You said biased
It's biased.
and several loss of information.
There's loss of information, and we don't use it to make decisions in inferential statistics. But it has some good things, right? It will actually show up in the data set in the discrete case, and it's the most probable value. All right. But know that for both the median and the mean as well. So what theoretically is does the median always show up in the data set?
No.
No, only if you have an odd number of values, right? If you have an even number of values, you take the 2 middle ones and you average them. And only if they're the exact same value will it be a number in the data set. But it is nice because it's literally the center of the data. The same number of people are above and below it. The exact same number of people are above and below the median. So that's sort of nice, which means it's robust to what?
Like obscure numbers.
Extreme values.
Yes.
Extreme, I think is probably I know exactly what you mean, but I think extreme. It is robust to outliers, meaning it is not influenced very much by outliers. The mode, it just moves over 1 for every. So if you start with something that ought to be normal, right, and you start adding extreme scores only on one side, we call that skew, right? And the median only moves over for every extra extreme person that's only on one side, right? So it is robust to outliers, as is the mode. The mode is completely unaffected by outliers. It doesn't care. The top of the mountain is always the top of the mountain. You can add extreme scores to only to one side all day, every day, and the mode will be completely unaffected.
The mean is the one that completely.
That's right. But the mean, a bad part about the mean is completely affected by outliers. And it's sort of like a give and take. It's a cost-benefit situation. The mean has no loss of information. It's a number that represents literally everybody in the data set. Right? So there's no loss of information, but a downside to that property is that it gets influenced by outliers, if there are any. It moves in the direction of the skew. But the mean isn't biased, right? The median's not biased, the mean is not biased, right? We only talked about the mode being biased. The mean is not biased, so we don't have to use any correction factor when we calculate it, right? No correction factor needed when we calculate the average. Does the average always have the same number of people above and below it?
No.
No, but it does balance something, right? What does it balance? The actual stuff that you're measuring. The deviations above the mean on whatever it is you're measuring, and the deviations below the mean are balanced. It's the one number, in fact, that balances the values above it as the values below it. So if you calculate a bunch of deviation scores, the negative numbers and the positive numbers will always cancel each other out, right? The average of the deviations will always be 0, right? Remember that? So know the good things and the bad things about the mean, median, and mode. So when we're calculating the standard amount of deviation, right? Conceptually, what we're trying to drive at is this idea is, okay, so if there's an average, let's say I look in the United States as a whole, the average income is $40,000 a year. I might say that the standard deviation is, I don't know, $100,000. Because even though the average is 40,000, there's a whole lot of variability. Lots of people are very different from the average, right? But then if I say in like the Amish community, the average income is also $40,000 a year, but the standard deviation is only 1,000, that means most people look really similar to that average, right? Does that make sense? Good. And so conceptually, that's what the standard deviation is. It's the standard amount of deviation. Very similar to an average, the average amount of deviation, except we can't actually get the average about, because it will always be 0, right? So what do we do mathematically to get rid of this problem? We square. We square our deviation scores, right? We square those deviation scores, because if we don't, our deviation scores will always sum to 0, and thus they will always average to 0. So if you've got the average deviation score, it'll always be 0, or darn close to 0, if you have rounding error. Very minor rounding error. And if you actually round it to many, many places, you'd probably find the place where you actually get 0. Does that make sense? All right, so squaring is super important. And so we get our deviation scores, we square our deviation scores, and then we get the average of those squared deviation scores, right? Right? If we have a sample, it's a corrected average, because we use n minus 1. If it's a population, we simply get the average of the squared deviations, right? But then there's one final step. What is it? To get the standard deviation. Take the square root to put it back in the original units of measurement. Because I don't want squared dollars. I don't even know how to interpret that. Right? If I'm thinking about income. I want to know the standard amount of deviation in the original units that I was measuring in. If it's dollars, if it's scale points from 1 to 7, if it's the number of pets you own, whatever it is. When I say that the standard deviation is 2, and I wanted to know how many pets you had, I want 2 to mean there's a standard amount of deviation of 2 pets. Does that make sense? Not squared pets. Right? What does that even mean? I don't even know. And so know the formal definitions for both the variance and the standard deviation. Know the conceptual definitions, what we're trying to get at, but also the formal definitions, the mathematical definitions. Right? The variance is an average, right? The variance is an average. The standard deviation is the square root of an average, right? What is the variance an average of? Is the variance the average of the deviations? What is it the average of mathematically?
Ask the question again.
What is the variance an average of? What are you averaging?
How much it varies?
The squared deviations around the mean. That's what it is. So know the math, and the mathematical definitions are in the lecture notes. Just make sure you know them. So the standard deviation is the square root of what? It's the average of the squared deviations from the mean. Know that. The variance is an average. Is the median and mode, are those averages? No, those are measures of central tendency, but they're not averages. They're different measures of central tendency. And the variance is an average. It's just a special average. It's the average of the squared deviations around the mean. And the standard deviation is the square root of that to put it back in the original units of measurement. Why shouldn't we use the range? Like, why is that probably the worst measure of variability? It's so much easier to calculate than the standard deviation, right? Yeah.
Because any outlier extremely affects it.
That's right. It's set by the outliers. Any outliers, you're going to have a very, it ignores everybody in the middle. Outliers have a huge effect on the range. Know the different types of graphs and when you should use them. The 3 types of graphs that we used in here were frequency graphs, histograms, and density plots, right? So when should you use a frequency plot? Should you use frequency plots for things like reaction times?
Frequency graphs.
Or frequency tables. Frequency tables. What, should you use them for reaction times? No. So for truly continuous variables, would frequency tables be a good idea? No. So it's going to be discrete variables with a very limited range, right? Many psychological variables fall into this camp. But a lot of the things that we measure don't. definitely know how to interpret graphs, right? Histograms and density plots, what's along the x-axis? Density is actually along the y-axis. How tall, frequency or density are just two ways of saying taller graphs or taller bars mean more people, right? But that's being tracked along the y-axis, right? You're going up the y-axis to see how frequently this score occurred, right? Along the x-axis is what?
The range.
The actual values, right? The actual values. And if it's a density plot or a histogram, then they need to go in order from the least to the greatest, right? Negative numbers are on the left, theoretically are on the left or the right. Greater numbers or positive numbers are on the right. That's just by convention. Think of the x-axis with density plots and histograms as the number line. The number line is there of your actual values. And the y-axis always tells you whether it's a histogram or a density plot, was this a very common score or is this a very uncommon score? Make sense? Yes.
So histogram is frequency, and then for density plots, it's density.
Density. That's the only difference. A density plot is really a smooth version of a histogram where you assume an infinite number of people. That's what it is. You extrapolate out the probabilities from the frequency plot. You extrapolate out the probabilities from the histogram of the actual sample you have, and now assume an infinite number of people. That's what it is. And so you put density or probability on the y-axis for a density plot. So I would know the characteristics of normal distributions, uniform distributions, and skewed distributions. Bimodal distributions, those are the 4 different types that we covered. Very common distributions of data. Know how the measures of central tendency and variability relate to these common ways that data can be distributed. Right? So any symmetrical distribution means the left and the right-hand side are the same, right? And that means the mean and the median will always be the same on any symmetrical distribution, right?
And the mode.
Pardon?
The mode be as well.
No, because think about a bimodal distribution. The mean and the median are directly in the center, but the modes are 2 of them off to the sides. So, but for the most part, unless it's bimodal, if you have symmetry, generally all 3 are the same, but except in the case of the bimodal distribution. Or anything where you have many peaks, then you don't have the mode being the same as the median or the mean. But any symmetrical distribution is going to have the mean and the median be the same. In a normal distribution, tell me about the mean, median, and mode. In a normal distribution. They're all 3 the same, right? They're all 3 exactly the same. Because if the left is the exact same as the right and the peak is in the middle, well, the most probable score is also the number that balances the values of the data, and it's also the number that balances the people above and below it. One of the neat things about a normal distribution is the mean, mean, and the mode are exactly the same. All right, so how are the mean, median, and mode affected by skew? Yeah, and what does that mean? I know.
It draws like it's at the center of all of the values, so if there are outliers, then it'll go towards them.
Right, the average goes towards the extreme score. Is that what you're going to say?
Yeah, the mean goes most towards the skew, the median next, and the mode is not affected.
That's right. And so remember, the mode is always the top of the mountain. It's always the highest place on the graph. The median will move over for every new extreme score you have, and then the mean, it gets dragged as close to those extreme scores. And so, oh shoot, I didn't bring a marker. Let me go. I want to draw some distributions on the board. I'm going to go grab a marker. I have some right now. Let's just pause this.